What I am is a Twitter dweller for many, many years, and I have collected a list of folks who I personally wanted to follow to kind of see the updates as they roll out. And we've seen many, many things roll out very quick with a lot of confusion and different application attempts from different places. And so I just compiled a list for myself, started following. RTAPS had incredible content diving into the timelines. I found, I want to introduce Sang Hyun. Am I saying this right? I think you need to hit the mute button and unmute Sang Hyun if this is your first time talking on Twitter Spaces. Let me know if you're able to do that, and if not, we'll try to solve this. And as I was collecting folks and around getting interested in this topic, and then how kind of what you found so far.
Material that they saw a ghost of a trace of in 1999, and he passes, and they have no money. Basically, this is kind of one-dimensional superconductor, and he had this theory.
So
maybe, do you want me to help Sang-hyun?
Yes, please.
Okay.
You have read my write-up, so maybe you can explain what's going on.
Okay, so I'm just gonna just to preface everything. I'm writing a work of fiction, so all of you guys are just participating in an experiment. So, but I'm trying to keep everything to kind of like factual, and trying to interpret what is kind of happening on the ground, right? Sang-hyun is much more factual, and he has actually been doing primary source work. So he's been actually digging up the actual Korean language science papers. He's been sitting down with friends. They've kind of summarized, kind of tried to understand what's going on, and he's really the one that's put together this the mentor whose name I think in some transliterations comes out to TS chair, some Dong-sik. The mentor was basically in superconductors in this idea of this kind of one-dimensional superconductor, and he had this theory.
So the name is Choi Dong-sik.
Choi Dong-sik.
Yeah, Dong-sik Choi. He was a professor in the Korean University's Department of Chemistry.
Yeah, and so he had this idea, this theory, and he had graduate students. And one of those graduate students was Lee, and Lee kind of took up the mantle of this theory, and then they tied up with Kim, who was an experimentalist, and then they kind of discovered this ghost of a trace of a material in 1999. And at that point, what happens is, having discovered this trace, their path kind of diverges, and Kim, the experimentalist, goes on to do a master's not in superconductors. So he does his master's in something else, and then he does a battery materials kind of PhD, and he graduates in 2008. While Lee continues on the superconductor path, does experimental, and when he publishes his PhD, it's both a theory and synthesis of superconductors. And then he graduates, and then he goes to work as a computer science adjunct professor, which Sang-hyun just found out, like a computer science adjunct professor, and he's there for about 4 or 5 years. He doesn't publish, and I'm guessing at this point he kind of gets cashiered out of academia completely, and he sets up a consulting firm, basically Q Center, and they start taking on consulting work. And then again, the timeline is a little bit unclear on whether or not they continue to work on the product, on what they discovered. And what happens then is in 2017, Choi Dong-sik passes, and as he passes, he gets his former students together, and he asks them to finish off what they started, to find this superconducting material that they saw a ghost of a trace of in 1999. And he passes, and they have no money, basically. Sang-hyun has done, again, primary source research, and the office space is basically like a 2-story building, somewhere in Seoul. It's a very modest kind of office. They don't have much money. My guess is that they need Kim, because Kim is the experimentalist, and I'm guessing also that none of the theory works at this point. The only thing that they have to go on is that they actually did find something in 1999, and Kim, I'm guessing, is also quite practical, because he didn't pursue the superconductors for the PhD, right? Because he's quite practical, he's like, dude, you get me money, I'll join you. You don't have money, I'm not joining you for your wild goose chase, right? So Lee goes out and he recruits Kwon, and Kwon is kind of like, he's a US PhD, he has a research university position. They recruit him and they get funding. And I think Sang-hyun, you were saying that Kwon is the one on the National Science Foundation of Korea's list, grant, right? I think that's what you said.
So the paper mentions the public grant from South Korea called the National Research Foundation, which is like a National Science Foundation in United States, and Kwon is listed as a primary investigator, PI. Is that right?
Yeah, that's right. Okay, so he's the PI. So they recruit him as the PI, and J.H. Kim, who is Lee's partner, basically leaves his very comfortable position as a research director in a hearing aid.
Yes.
Yeah,
the company is called ICELTEC. Called ICELTEC, and it manufactures the battery specialized for the hearing aid. So it is a medical device. They have different standards from other batteries. And the company is a small business in South Korea, but seems competitive worldwide.
So he leaves.
Let me intervene just real quick and just to give folks a quick summary. The main paper that we saw the explosion from, that was published on July 22nd, so a week and almost a day, so we're like almost 8 days into this. The 3 people that you just said, besides the first professor Choi or Chair, I'm not sure, several places write it separately. So the 3 people, Fakbae Lee, Ji-hoon Kim, which is the LK in LK99, right? Lee and Kim, and the third person you just mentioned is Young-Wan Kwon.
Yes.
Those are the 3 authors on the paper that kind of was published on ArXiv out of the blue 8 days ago. Please continue.
Right. And then, so at this point, they're in 2017, and Lee goes out and does the fundraising. He recruits Quan, who's a research professor. Quan is basically, he's on the paper. He's the principal investigator on the grant, but he's still a professor at university. So he's basically, I'm guessing, like a day in the in the office at Q Center. Very modest place. I think the grant size is pretty small. And they get this ESR machine. And again, from what I can tell, the ESR machine, only Kim knows how to use it, because none of the other people are actually synthesis people. They're all like theory guys. Quan is a physicist, and Kim himself, J.H. Kim himself, he's looking for something which you have to know what you're looking for, right? Because that's what he says in his LinkedIn. He's like, I'm looking for something. If you don't know what you're looking for, then forget about it, right? But he knows what he's looking for, and they refine, and he keeps doing experiments. He keeps refining the experiment, and it goes through like 1,000 iterations. And somehow, starting in 2018, somehow by the middle of 2018, they find it. So that's a surprising thing for me, because I suspect they've been working on it, before, or Che and Lee had a breakthrough on the theory, so they knew how to narrow the workspace down. But somehow, at the end of the day, Kim is the one grinding through the 1,000 experiments, finally to get a sample that works. And then they start.
No. So besides the two papers, there is a paper published in April, written in Korean, and in their own words, they describe what prompted their breakthrough in 2018, and it said that so they are putting the material in a quartz tube, and because they cooled it too fast, the quartz tube quenched and broke, and the material left after the breaking of the glass was had the property they wanted. So it was an accidental discovery.
So can you repeat that? Like what happened? They put it in the quartz tube, and the quartz tube broke accidentally?
Yes.
I see.
And that was the breakthrough in 2018.
I see.
What I say. Yeah.
I just want to confirm what I hear. The breaking of the quartz tube led to the incidental discovery. This is the breakthrough as it's written in the first paper in Korean?
Yes.
Okay, so I'll just call ATAP, just give me a sec for some logistics. Folks, if you look up on top of the space, there's a few tweets we're pinning, and as we go along, we're going to add some information on top of this. The third tweet pinned from Dystopian Breaker has a link to the original kind of Korean paper. So please go ahead, ATAP.
So quick point.
Yeah, go ahead.
This could be important because as soon as you expose it to the atmosphere, you're potentially getting hydration, and hydration might be harmful, might be helpful. From this like little account, it seems like it either didn't do anything or was helpful, but like knowing what temperature it was at when it broke and things like that could actually be really pertinent.
Yeah, so absolutely. Like, so it's not, he does do the 1,000 experiments, but the 1,000 experiments, whether that gets him there or not, at one point in the experiment, the quartz tube breaks. That gets them there. They get lucky, right? So they get lucky. And then after that, things proceed pretty quickly. They isolate it, and then they get the crystallization. They start working on the papers. They start working on the patents, and they start also trying to figure out the chemical vapor deposition process. They seem to have made some headway on the chemical vapor deposition process. And then, sometime around September 2021, some things start happening. Quan takes a position, a sabbatical at, I think, Seoul National University at that point. I'm not sure whether that means he's putting more time in the office or not. And then that fast forwards to, go ahead, Sunghyun.
No, you go ahead.
Okay, so that fast forwards to about March 2023, when basically the international patent has been filed, and Quan leaves the team at this time. I'm not sure when Hyung-Tak Kim comes on board. That's not very clear to me at what point Hyung-Tak comes on board. So I'm guessing it's after the nature paper gets dinged in 2020. And the other thing that strikes me also is that every single person on the team is very aware of every single hoax in superconductors to date. Right? They all know the space well. They've seen every single hoax before. They know what the hoaxes look like. They know what to look for. They know what diamagnetism is. So I don't think. Yeah, go ahead.
So the date is. So the day before yesterday, Andrew McCauley posted on his Twitter the translation of the Korean paper at Doctroid. Is that correct? And can you? So how did you translate it? Can you say something about it?
Andrew, I think he's referring to you. Some kind of referring to you. You posted a translated paper also, right?
Yes. Now that was just a machine translation from Google. That was just a very cursory translation.
Okay.
So basically, Quan leaves the team in March, and then you have the kind of papers being released, haphazardly. The next point that we know of them is that they start releasing the papers haphazardly, like late last week. And then we have.
And by they, I think it's important to highlight. By they, Quan, the guy who's no longer affiliated with Q Center, like this whole endeavor, a business venture that's funded for this purpose. Quan is no longer affiliated with that. We've seen Sunghyun posted an interview in Korea from Friday where I think both Lee and Kim say that Quan, the guy who published the first paper, is no longer affiliated. There was some speculation as to maybe the limit of 3 people on the paper is the limit of the Nobel Prize, where Nobel Prize limits to 3 authors. I don't have this confirmed. There's speculation going around, and it's important to note that like both of them say that the paper was not ready when it was released, and it was released by Quan, the guy who left the first paper. 2 hours later, 2 hours and 20 minutes later, another paper gets released in the same archive with, I want to say, 5 authors, not including Quan. right? So Lee.
Yeah,
And,
and the username is Hyung-tak Kim, the college professor from Virginia, is the username who pushes the artaps paper at that point.
Yeah, Hyung-tak Kim is a big name with the H index of 45. And if you look at the paper, there is an error message in Korean saying that bookmark could not be found, which is a usual error message when you did some of the typesetting wrong. And you just don't publish the room temperature superconductor paper with the error that says bookmark cannot be found if you are hurrying, if you are not in emergency.
So it does feel to us, at least from the summary so far, that the paper that Kwon released has different information than the second paper, and the second paper feels like it was released in a hurry and included more people that currently work at Q Center, including Hyun-tak Kim. And Sung-Hyun, I want to ask you this question. You mentioned his H score or something score. Can you explain the importance of that score for Hyun-tak Kim?
Please, someone else do the explanation.
Okay, so the H score is, because we have a web savvy audience here, it's kind of like a page rank for researchers. It shows you how influential the researcher was, and so a higher score means that more people have been citing your paper.
Go ahead, Ben.
Yeah, more precisely. So like an H index of say 40 means you have 40 papers that each have 40 citations or more. That's a little tricky to understand. So like if I get another paper that has only 30 citations, it won't affect my H index at all. I have to get a 41st paper that has 41 citations to make it rise.
So I think it's safe to say that Hyun-tak Kim, the guy who submitted the second paper, potentially haphazardly, correct? Like we're saying there's errors in the second paper 2 hours after the first one, so likely prompted by these events, is a cited, very well cited scientist with a very high kind of confidence score. It's not like a random person of the street that decides that there's now a superconductor of room temperature and verified it.
Okay. Sorry for being sidetracked, but I just checked the machine translated Korean paper uploaded to Doctoroid by Andrew, and on the page 5 it clearly said that the quartz tube was destroyed due to internal pressure during rapid cooling of reaction and etc. So I think, in fact, nobody really read it carefully. It is just there about the quartz tube was destroyed.
Yeah, so I think it's definitely, like, probably the rest of us are not very close readers of that paper.
So we can continue on after the upload to the archive.
Indeed. So okay, so it goes into our archive, and then all of the events of the last week happened. I don't think any of us expected any of the events to happen. So we've all just been kind of like following along and seeing what happens next. I had no idea that there was a metallics conference in South Korea, and I definitely had like no idea that one of the authors would show up there. And it gets posted on Twitter, and so and then Seung-Hyun points it out on the FM Korea football message board, and so we translate what the audience reaction was in a bad translation to get. So
if you don't mind, let me interject here, because this is around the time that I found out about this. Alex, Frozen Coffee Alex, I forgot his nickname. We invited him here. He posted a very long Twitter thread that got the attention of the algorithm and then boosted of this room temperature ambient pressure superconductor paper from Korea. I think he only started talking about the first paper, and then after the second paper also came out. And I think at this point, or somewhere around there, Andrew, you found out about this. When did you first hear about Twitter drama around LK99? And Andrew, feel free to please introduce yourself officially and Varda and how you're interacting with this.
Yeah, so I was just cruising the internet at night, and this came across, I think, my Twitter feed. And so I'm incredibly curious. This is something that has been a bit of a hobby for me. And so I was always interested in superconductors, so it caught my attention. I'm a mechanical engineer, so full disclosure, I am not a subject matter expert. I am simply an aerospace engineer that has a lot of curiosity and some assets at his disposal. And so reading this paper, it struck me just the simplicity of the process. And so I realized that I probably had the ability to replicate with full fidelity the process that was described in the paper. And so that within about 30 minutes, I realized I should simply start down this road that Twitter was already picking up at the time. There's some conversations going back and forth, and it was the classic scenario where on every superconductor discussion, there's the same conversation that happens over and over again. And this synthesis appeared so simple that it seemed that the most expedient thing was to simply test it physically. And so my work is very receptive of after hours projects. I'm known as the guy that has really aggressive hobbies, let's say. And so I'm always in the back doing something interesting with materials or automation. So within 30 minutes of reading the paper, I had kicked off orders to various chemical suppliers. I'd reached out to overseas vendors to try to procure a couple of the elements. And so it was just kind of an offhand comment that I made on Twitter, and then the ball really started rolling. And I realized that everyone wanted to see this made. And so it was just supposed to be a fun little project, but I was really overwhelmed by the response. Everyone wanted to see this done. I think there's this incredible curiosity. There's this incredible drive. People want to see like incredible things happen for the human race. And so something of this magnitude pops up, everyone's motivated to drop everything and investigate. And I think that's where we're at.
And I think you met the algorithm at the right place where folks were excited about the future and think this could bring a lot of changes around the future. And you started saying, hey, here's a direct approach. Let's try to replicate this. And I want to just highlight the fact that the materials involved in creating this and the process. Some folks say, and please talk about this, some folks say that had this been an attempt at a hoax, it wouldn't be as simple. They wouldn't have released a simple instruction manual, kind of quote unquote simple, that many labs around the world will have to get given the materials and the right equipment, right? So the straightforwardness of this potentially shows some stuff.
So this is a good time for a PSA. I mean, I know that Andrew is well aware of this, and many of the people who've been following it. But in case anybody who's listening isn't, these compounds in vapor form, at any rate, are highly toxic, and you have to know lab safety if you're going to start trying to experiment with them. You need things like a glove box and all kinds of PPE, a fume hood, everything else. Taking risks with this kind of thing is just really not worth it. I can't stress that.
Definitely.
Absolutely.
Don't try this at home, kids. Definitely.
Yeah, absolutely. There was a lot of chatter in the beginning, in the first couple hours, about this can be replicated in a garage. And, I thought it was interesting. I thought maybe we've got the opportunity to do it safely. We've got all the right equipment. We've got the millions of dollars of equipment to support our spacecraft business that allow us to do some of these things safely. And so I thought, Twitter wants to live vicariously through somebody. Why not do this? I ended up being in sort of an interesting middle ground because I'm not in academia. I'm also not trying to commercialize any part of this tech, really just doing it for fun because it's incredibly interesting. So I've got no skin in the game except for making this work in a transparent manner and then getting the materials into the hands of the experts. So I thought if we can leverage some of our equipment and some of our very smart people that we have to speed this timeline up. I didn't see anybody in the United States being vocal about trying to do replication. There are so many stories coming out of other parts of the world that all the labs, there must be thousands of furnaces burning right now trying to replicate this. But I wanted to get material into the hands of some local experts in California. And so that's really our goal is, can we sort of be the face of the internet, do this experiment in a safe manner, and then help advance the science and be sort of a forcing function to doing this replication.
So Andrew, just before, just a small pause before you continue, I want to ask the other Andrew here on stage, Andrew Coe, if you're able to unmute and talk to us, if you're available, about the potential reasons why all of Twitter jumped on this. Andrew Coe, you had a thread on room temperature superconductors, 2 weeks before this, like almost a premonition kind of thread. And could you give us some summary? First of all, feel free to introduce yourself, but also some summary of what this means if this replicates, what this means for the world, applications. Can you give us like some excitement of what happens if this is an actual ambient pressure and room temperature superconductor? Andrew? Does not look like Andrew is.
Okay, sorry, my audio cut out for a second. I missed the prompt.
Oh, there you are. You
sure, yeah, thanks.
Folks, I explained to folks your thread about ambient, pressure room temperature superconductors that you've authored 2 weeks before the paper came out, and then suddenly this drops. And I wanted you to highlight some of the potential applications of superconductors and give us some of the highlights of what happens if this replicates and this is an actual, real thing.
Yeah, sure. So it's kind of a funny thing. I put that thread out there 7 weeks before this story broke. I have worked with this kind of stuff in a few different areas now. So it's very, superconducting radio frequency cavities are standard technology in accelerator physics. It's a field I used to work in. My first job in physics was actually in a condensed matter lab using a scanning tunneling microscope to look at, electronic structures of potential high temperature superconductors. So this has always been sort of like a holy grail of material science, sort of a holy grail of applied physics. It's one of these properties, it's one of these materials where the bulk properties come from its quantum mechanical behavior. And when quantum mechanics and its effects escape the realm of the very tiny, it can really manifest as magical phenomenon at our scale in the world of the kind of the bulk matter, the big stuff. So, superconductors are used currently today. They've reached engineering applicability through decades of continuous refinements and improvements. And some of the biggest things to think about in what lets these things get used in industrial applications is their ability to superconduct at higher and higher temperatures. And also importantly, is to operate at higher and higher background magnetic field strengths. And so the way to think about this is that a superconductor, it's allowing current to move through it with zero resistance, but it also perfectly expels magnetic fields. And there's an operating point of these materials where it's basically the current density and the temperature and the magnetic field kind of put the bounds or the performance envelope on the material. So some conductors can carry tons of current, but they can't exist in a very high field. And so, those are hard to make as useful. You can use them for carrying like electricity, which is awesome. But often what you really want to do is generate very strong magnetic fields. So I think maybe the most familiar to most people here would be like an MRI machine, right? Magnetic resonance imaging. So the idea there is you're generating a very high strength field, and magnetic fields are measured in Tesla, for example. So just for context, 3 Tesla is a pretty strong field, and that's what is about the strength used in an MRI. So MRIs use these cryogenically cooled magnets, or they're not often cryogenically cooled; they're actually often just copper, but they do have cooling. But they generate this high strength field, and then it kind of sets all these little protons in your body spinning and dancing in a little kind of radiating energy. And then you have a pickup coil, which is like an antenna, and the antenna is trying to pick up that energy and kind of reconstruct what's going on in your body. And this is how we can get like a really high detailed, high fidelity, 3-dimensional image of what's going on inside someone without any invasive surgery. So it's like MRIs are a real kind of amazing breakthrough in medical imaging. Superconductors, if they could work without cryogenics, would really simplify and make cheaper and more available high resolution, high fidelity 3D images of people's bodies. Not just for making the magnetic fields, but also for picking up the signal emitted by the protons that get put into motion by the field in the first place. So it's kind of like one sort of off-the-shelf example. I think another one that's kind of under the radar we don't think about it's not just in carrying electricity without resistance, which is useful for long-range like energy transmission, that kind of stuff. But if you look at the national grid, I mean, only 5-7% of energy total, which is still significant, but it's single-digit percentage, ends up burning as waste.
You're suddenly muffled.
And I think, yeah, suddenly your voice like you're.
Oh,
better.
Now it's better.
Okay, sorry about that. Yeah, so I was going to say, so national grid scale energy production, right? So transmitting the energy to its endpoint consumption. There's a bit of waste heat along the way. But what's also important to think about is how that energy is produced. It's produced also using high strength magnetic fields. And I was looking into this. There's a experiment where these guys used sort of more modern high temperature superconducting tape to retrofit a large DC generator, and then it had like a 36% power improvement, right? Which is pretty substantial. That's a serious win. Yeah, so there's sort of thousands of places this stuff could be used that would really just it would either greatly improve the performance, efficiency, reduce the cost, increase the accessibility of what we think of as like high technology like MRIs or particle accelerators. But it would also just decrease the cost of basic things like electricity generation and distribution. And that's just the beginning, right? So, this kind of stuff, there's a really good analogy here actually with a transistor. For years, scientists, biological engineers, and physicists, they had this idea of a transistor, right? If only we could have some kind of simple, reliable current multiplier, we could design all these wonderful things. We could design all these different kinds of logic functions and so forth. And so there was this search for the transistor. Like people were searching for something that could do that. And they had anticipated all the places it could be used ahead of time. And it wasn't until at Bell Labs, a very kind of funny crossover here. One of the guys that's on the patent for the transistor is John Bardeen. And John Bardeen is actually the only guy to win 2 Nobel Prizes. One was for the transistor. The other was for the theory of superconductivity, right? Which is Bardeen-Cooper-Schrieffer theory, BCS. So again, it's one of those things where physicists, scientists, engineers have thought of this for a long time, realized this could be amazing. And there's been this, really complicated random walk through the configuration space of possible materials, right? Which is so high dimensional. There's so many possible things you can construct. So I think I'm very optimistic about the field in general. I think one thing to think about with this particular result, there's so much artisanal craft and mastery that goes into producing these materials in a reliable, consistent way. Science, people don't often recognize it's a lot of art involved too, right? Like things that are reduced to expert practice and know-how. And so I'd just be cautious on, jumping to conclusions either on this particular result if it's valid right now, but also if some labs can't fail to reproduce it, it doesn't actually rule it out entirely. I think there's some scientists that travel to Korea to work with the original authors. I look closely at that. I'd also, my internal odds are kind of like a 1 in 6 chance this pans out, and it could be big. But that doesn't mean that it's the end of the search or the end of the race. And I'm also optimistic that getting people to understand what the massive long-term and large-scale social benefits of this kind of discovery could be could help direct a lot more basic science research towards this field. I think we spend a lot of things on like how to make smartphone cameras better, and not a lot of things on, and not as much as we could spend on things like high-temperature superconductors. And just as a final example, so right now, I work as a stellarator engineer. Stellarator is a type of magnetic confinement fusion reactor. The reason the company I work for can exist, and the reason there is this current boom in nuclear fusion, is because we've engineered these high-temperature superconductors to work in higher and higher magnetic fields at higher and higher temperatures. And the big economic breakthrough there came when we can have these superconductors that can work at liquid nitrogen temperatures, right, which is 77 Kelvin. And it's a lot cheaper to make liquid nitrogen and run that kind of cryogenics than it is like liquid helium at like 4 Kelvin. So, we're already reaping some of the benefits of this sort of tech stack maturing over time. And I think it's really just getting started in terms of like the hunt for promising materials. I'm hoping this results in positive publicity and more effort, more energy put into the field. I think if this doesn't pan out as the thing, don't give up hope, right? This is a long-term game. Science proceeds by starts and stops. There's no fundamental physics here that's impossible, right? There's no physical principle that says this can't work, right? This isn't like a momentumless or massless propulsion drive like the EM drive. This isn't like superluminal neutrinos, right? Those things kind of break laws of physics. This is very much in the realm of, physically possible. Seems very, in my mind, seems likely there could be something out there, given the complexity of state space of electronic structures and given how large that space of exploration can be. So I think I'm just kind of, this is a great time to be interested in material science, to appreciate basic science research, and educating ourselves on how good the future can be. I think there's a lot of narratives right now in society and culture in general that kind of say like, we can't solve our way out of our biggest problems today, right? And I'm very much on the other side of that debate. I think we can. I think it's through efforts like this. I think it's through people like Andrew and Varda that are willing to do stuff in their backyard or their garage or the fact or their workplace on their extra time. This is the let's build mentality, right? And so I think we can build our way out of the world's greatest problems. And I think it's fundamental scientific advances like this discovery could be that kind of pave the way out of there too. So overall very optimistic.
Andrew?
That's incredibly well said. That is incredibly well balanced viewpoint. So how would you advise people to absorb the next week of the news cycle? We're very much on a, we're back, it's dead, we're back type of hype cycle. So how do you advise people to think about the results that they're seeing, knowing that this is a very difficult thing to replicate? Just because a negative result is shown in a lab, that doesn't mean it's not physically possible. It's very difficult to prove the negative here. So tell us how we should absorb the news cycle coming up in the next few days.
So I might say something about that. I think this is basically tacit knowledge transfer, and Kim seems to have been this kind of like artisanal experimentalist. So you need people to actually sit there in the lab with this guy, and he needs to demonstrate to them. And they need to pick up, and there might be things that he does which he didn't write down. That's like my take on it. Given that he's the experimentalist, he's a synthesist on the team. Given that the team seems to have been only like 5 or 6 people, is that this guy is maybe the only person in the world as of 18 months ago. I'm guessing that he managed to transfer some of that to the HumeTux team. So I'm guessing that at least one more team on Earth has this now, and I'm guessing that this knowledge transfer is now happening to a couple more people. So you need to see this progress maybe 2 or 3 cycles for like a bunch of other people who have learned the skill, and then that's when things get interesting.
You don't really need to replicate to verify this. The team has the working samples. They can just samples to the labs around the world.
Well, that's true, but this doesn't help us if it's unobtainium, as far as every other group is concerned.
So we heard rumors that they are willing to send samples for the serious experimental groups, and in fact, they are already shipping samples. That's what I heard.
We also we have somebody who's in the audience, and welcome to come up as well. Jesus Lars, I think, from physics at MIT. He had a thread about somebody, his colleague, who's already over there. Apparently, there's kind of already folks looking at, and Jesus, you're welcome to come up. If you just DM me, welcome to raise your hand and come up. I'll find you and talk to us about your colleague. But apparently, there's like at the point, there's already research happening, and folks are like reviewing this. I would also say to add to what Sang-Hyun said, the authors, at least the second paper author, is not one who's hard to reach, and we'll talk about the metal convention. Sorry, I'm eating my words. The metal convention that happened on Friday, where Juan presented this research could have been the reason why he released the first paper. The author of the second paper also said they're willing to work with folks, so they do shade on the kind of the release process, but not the science within the paper, right? So it looks like both folks who work there, they definitely, sorry, both the kind of the first paper people and the second paper people, they all believe in the science, and unlike the previous attempts at superconducting days, if I'm not mistaken, this seems like everybody here, some of them are very credentials, like we said, all believe that this is what they have. And I just want to add additional points, and then I want to acknowledge more folks on stage, is that some folks are throwing around if it's a diamagnet, and if the results are everything, like it's just a diamagnetism result. I would love for some folks on stage to tell us what this is, but also the people who work there, based on their credentials, based on the papers, seem to know the difference between just like a regular diamagnetic effect and a superconductor, because they've been working this for a long time. This does not mean that what they have is what they claim, but it definitely means that this is, like, we're trying to peel the onion here from the layers of the onion based on very limited information that we're able to get about whether or not this could be replicated. But at least we can look into whether or not it seems like a fake attempt or a fraud or something like this. And a lot of the things that we've covered here before, the process, the two papers, all of them trigger this like almost a gut reaction from the scientific community. Like, well, this is the paper doesn't have all the required materials, or the paper is not fully done, etc. We're trying to highlight why this potentially happened, and whether or not it means anything about the actual science or the actual achievement that they had. Sang-Hyun, you had a comment before, and then I want to recognize Jesus, who I saw the tweet from about the MIT professor that's over there talking to the folks. So feel free to Sang-Hyun and then Jesus.
So Ben raised his hand and wanted to speak.
Okay, so just before I get to Ben, if you don't mind, I want to hear from I'm hoping saying this right. Jesus, hey, welcome to the stage.
Hey, thank you. Yeah, you're saying it right. So there's two professors that I'm very close with from MIT. One of them is a physics professor, and he doesn't focus exactly on superconducting. The other one does focus 100% on superconducting. So when I heard about this, the first person I reached out to was him, because actually I wanted to try to replicate it, and he told me it was a very bad idea. And then he later told me he was actually in Korea, and he was going to ask them and his plan was to ask them for a sample, just so he could test superconductivity. And I told him, perfect, like, can I share your message about not replicating it? I'll keep you anonymous. And he said, yeah, that's perfect. So I did that, and I've been trying to keep him anonymous as well. And then I told him I would also reach out again to see whether he succeeded or not in replicating, and I sent him some more emails, but he hasn't responded. So I'm hoping, or maybe I'm guessing, he has more important things to do this time. Maybe it's actually succeeded. I don't know. But I guess my personal feeling is we can't really know until replication happens, or until someone like him actually tests it and it succeeds. So I'll definitely let you guys know as soon as I find out.
Thank you, Jesus. Thank you. Ben, you had a comment before? Go. Ben, if you're still here and you can unmute and wanted to go ahead, and if not, 85, go ahead.
Okay, so I have a couple of questions for anyone who might be in the know. So J.H. Kim mentions using a ESR machine to find the initial trace in 1999. What is that? Like, what is he doing? What is he looking for? And he also says later on that he's using this MMA process, like, and that no one else needs to knows how to use it. Like, what is he actually doing? What's actually going on there?
So I'm not familiar with the latter, but ESR is like electron spin resonance. It's a pretty standard technique in organic chemistry.
Right on. If anyone else has any ideas of MAMA, just put up your hand. Maybe Alex can pull you up. The second question I have is to all the scientists in on stage or in the audience. The paper submitted to RC, the second paper, the sixth author paper, has at the very end of it a kind of like a split of credits, where they're very, very specific, like so and so has equal split, so and so led the fundraising even, so and so, etc., etc. So and so was support on these items. So is that common in like scientific papers in even organic chemistry or inorganic chemistry in the West or in Korea? Like, how does that work?
It's a recent development. You see it in a lot of places. Some journals are starting to require it, I gather.
It's useful for parsing who is like a PI or one of the people who runs a lab on the paper and who's like actually doing the work. I think that's like one of the main utilities in it.
Awesome. And so I want to go back a little bit in our kind of research about the timeline, right? So what we do know that also happened on Friday.
I can maybe also speak to
go ahead.
The inorganic synthesis methods that they were describing. So I think the general idea behind that, again, it's kind of hard to using acronyms I'm not familiar with, but you have this material you synthesize, and it's not pure at all. It's probably a mixture of who knows how many phases. And you want to find, if you have a trace amount of superconducting material within that, you want to figure out, do you have that trace, and if so, what is it? And so they probably just synthesize batches and batches of this stuff, and then they run this technique to see if there's any superconducting material in there. And if they do, they think, okay, well, I did this synthesis slightly different than the other ones. So what phases might there be more of in this batch than the other batches? And then you can refine your synthesis and get closer and closer to some batch that has like more of that phase material. I really think that a big problem. So I'm on these email chains of people trying to replicate this from the Superconducting Quantum Materials and Systems Center, which is based around Fermilab, and Argonne National Lab, and Northwestern. And the inorganic chemists seem very skeptical that the material that they say they made is indeed what they made. Basically, they are not making any value judgments on whether they do have a superconductor, but they don't think that based on the synthesis they described, they would get that structure. They just don't think it's physically possible to get that through the synthesis they described. And simultaneously, the theoretical people don't think that the mechanism they've described makes sense given the synthesis and that it's superconducting or supposedly superconducting. So whether or not they have what they think they have, I think people will kind of see. I think it's important if they give these samples to people. I think the best thing to do will be to just put it in a microscope and do basically diffraction to completely index structure. Currently, they've only done X-ray diffraction, and that can tell you what the space group is. It's a little too technical, but it can tell you what the structure of the material is. It doesn't tell you what type of element is in each of the positions, and that's crucial.
So just a follow up on that, Seong-hyun, how much was the grant from the Korean National Science Foundation for this project? How much money did they have to work with here?
So if you are a researcher in South Korea, you can search for the grant number and get all the data. And I have numbers, but I don't have it at hand. I don't have access to the system, but my friend had, so I received everything about the grant. But it's not a lot of money, but I don't know the exact number right now. I want to talk about the updates after the two papers were downloaded to archive in a chronological order.
Before we go on, because we just touched on this point, there was the notion of trying to enrich for the right phase from everything else that you've got. I didn't, I could have missed it. I didn't see any mention of it in the paper, but on J.H. Kim's LinkedIn, one of the slides that he has alludes to it. He talks about separating stuff chromatographically and spreading it out as a film and analyzing that, and that's that latter method. And that actually is probably going to be critical to identifying the right phase, at least early on, as anybody's trying to optimize their synthesis. And I'm actually kind of multitasking right now, and I'm looking at papers where people are separating out superconducting particles.
And definitely, folks, follow Eli for updates on this. Seong-hyun, go ahead. You wanted to connect some more dots.
So the paper. So I found about this room temperature superconductor from Hacker News on Wednesday. It was on the very first item on the front page for hours, and I was especially interested because the researchers were from South Korea and I'm from South Korea. So like everybody else, I started to search with the search engine. And the thing with the search engine is that today machine translation works very well, and you can read for the materials in other language. But if you don't know the language, it is hard for, say, people who only know English to search for the Korean web. So the material was named LK99, so I immediately searched it for the Google Scholar and the Korea Citation Index, which is that every significant paper published in South Korea is indexed. And I immediately found the previous paper published in April, and I read the three papers. And the next day, I kept searching for the media report in both English and Korea. And on I think it's the Wednesday, on the first day, New Scientist interviews the Hyun-Tak Kim. And the next day, the first South Korean media to interview the team is Joseon Beat. They say that the reporter went to the office and met with Seok Lee. And on the third day, on the Friday, Seok Lee again talks with the Yonhap News, which is like the Associated Press in South Korea. And the very peculiar thing about these interviews is that Seok Lee is telling different story on the Thursday and Friday. On Thursday, it's like that the team uploaded to archive intending to publish, but on the Friday interview they say that it was not intended to be published. So I think what he said in Thursday is a lie to protect the secret that there is an internal conflict in the group.
I just want to add something. There's also, and I think we've covered this briefly, but there's the way I found it, at least on Twitter, is because on Friday there was an international materials kind of meeting consortium, which was international, but it was in Seoul, right? And we know that on the list of speakers, nobody talked about any superconductor stuff, but we do know that Kwon, the guy who published the first paper, is no longer affiliated with Q Center. He gave a talk at the conference, kind of simultaneously with Lee getting interviewed in the media. Kwon went to this conference and gave a talk, and even I think we have some folks on Twitter who actually kind of took pictures of the presentation. Could you talk about what you found out about the conference and what was said and what was shown or not shown, presented or not presented?
So it was a big conference. So multiple people in South Korea and abroad attended the conference and witnessed the talk. And many of them wrote about it because it's an interesting story. And the poster on FM Korea, Football Manager Korea, even said that he is writing this for karma because he knows it will be immediately aborted a lot. And he was right about that. So what story says in common is that people asked to see the actual sample and the demonstration of Meissner effect. And it is said that one brought the sample and it was shown, but no demonstration was performed. Why that is the case is unclear.
There's also something about a translator, correct? there was also something, this conference is international and English-speaking presentations. However, this presentation was translated with somebody else, and Kwon gave this in Korean. Is that, have you also seen this?
Yes. Everybody agrees that Kwon gave a talk in Korean and someone translated for him.
That's very interesting. Okay, so yeah, and then you're watching this news, you're reading the newspaper. You went also and talked with some of your friends. What more can you tell us from your research, from reading, from the stuff that gets lost in translation that you've picked up in several of the papers?
So this morning, me and my friends, other two people, so we are three people, were so actually most of the writing was done by Kang Sung-hoon, who is in the audience, and we discussed how to revise it and publish it. It's almost 3,000 words and it is hard to summarize. But the main point is that careful reading of three papers and context of its publication, we can learn from the various interviews and news articles and the incidents with the international conference, is that three papers are talking about completely different things, like the proposed theoretical mechanism for superconductivity is all different and there is no commonality at all. And why that happened is an interesting question, and I think we arrived at the answer that explains all the oddities of these papers. So after the space is finished, you may want to read about it. I mean, it is a long story. I cannot summarize it.
So I have an unrelated question for again the researchers out there. You know, again, being like, for me, and I think I've said this before, if you really had like such a wondrous material, and this stuff will let you see stealth jets, right? Like if you put it on your radars, you will be able to see stealth jets, right? So would there be some national security concerns about like actually doing like peer review and stuff like that? Would there be like governmental intervention to kind of keep it as a trade secret?
So at this level, I don't think this is not. I guess if you were working on like a patent, you know, an actual technology, not a patent, but an actual technology to do that, that might be ITAR or something, but not at the fundamental science level. That's not a concern. So,
hey, Robert, can you introduce yourself, please? Welcome to the stage.
Oh, hi.
Introduce
Yeah, I work in the aerospace.
As much as you can, yeah.
Yeah, I work in the aerospace field. I got hired out of my thesis where I was working on like cuprate superconductors, and I I never finished that thesis. But yeah, so I'm in the working on like aerospace manufacturing and like material science in that field. So yeah, so I'm a little familiar with that. Like if it's at the like basic science level, like we're at here, like that's definitely not like ITAR or EAR. If you're talking about actual like high performance materials, maybe.
For
but
folks
not
in the
just
audience,
samples and stuff. What?
For folks in the audience who are not familiar with ITAR and
oh yeah, just like export control. Like you're not supposed to just be able to sell missiles to whatever country if you're in the U.S. But that also applies to like technology and sometimes really advanced materials. So yeah, it's just like export controls over that. You have to go through crazy approval process to do that. But yeah, it doesn't apply to like really basic science.
So that's interesting, and I think the thing that interests me is because we know that there was already a paper published before kind of the ArcSci paper that Kwon uploaded, right? We know there's a paper published in Korean, and he left the company by the point where he published it. We don't know why. You know, the close proximity to an unannounced conference appearance could be one reason. There could be other reasons. The three authors of the paper and infighting about Nobel Prize. I think somebody in our group that said that also Chinese social media kind of has the same conclusion, where you know that's smoke. You know, potentially there's fire, but it definitely seems like smoke because if it's this big, then potentially there's some Nobel stuff. But this wasn't restricted information. That's what I want to say, right? Like the paper in Korean has many of the information here, and it was already published, like for everybody to just find. And also there was a patent applied for. I don't know if they granted the patent. Please correct me if I'm wrong. Also around April, or even before that, the patent was applied, and that also was like restricted.
So I can talk about patents. There are multiple patents applied, and one patent is granted in Korea. The very first one.
Hey, Sang-Hyung, I have a question for you about the samples, because I agree with you. Like the synthesis doesn't actually have to be. I mean, we're still just knowing if this is a real thing or not. Like that's the most important thing now, I think, not synthesis, replication. So do you know who the samples are being shared with? Because as long as the samples are being shared, it can be verified and replicated. Like we can know for sure if this is real or not.
I have no idea.
Just before you enter, maybe you have seen this or heard this. Jesus told us about a potential collaboration in potentially in the lab. I don't know, Jesus, if you can confirm whether or not the professor was there for the conference, because it just would make sense. But you don't have to. I know anonymity was promised, but yeah, we heard from a potential collaboration, or at least a request from from folks from I think MIT, and we also know that some folks on the paper said they would collaborate and even potentially share samples with folks who request this. Additional thing that's pretty much important to convey to everyone now that this information is out there. We have somebody in our group chat. I don't know if she wants to come up, but definitely worth following the list that I've kind of talked about. Elsa, she's following Chinese social media, and there's many attempts in China, and some of them were even live streamed. Wink at Andrew. Some of them were even live streamed, I think, today to also replicate. And this definitely goes back to Andrew Cote, where even an attempt to replicate, they will not, show the Meissner effect, or some properties. Does not necessarily mean that what they have is not a superconductor, right? Like it's not a complete negative.
Yeah, totally. I can just offer, some people on the call may be a lot more familiar with how patents work than how scientific publishing work. And so, an archive preprint submission, something that's not peer reviewed. I mean, just for context, science is hard, right? Most things are not reproduced. Most findings, most results are very difficult to reproduce, especially things like material science and especially life science. Doesn't mean that there's not scientific discoveries. It just means that the number of free variables is very hard to pin down. And sometimes scientists can't even reproduce their own results because they weren't aware of everything that happened. So that being said, in the patent application process, right, in the United States at least, there's a provisional patent application, right, and then there's an actually approved patent, right. So you can think of an archive preprint submission as like a provisional application, right. It's there to establish priority, there to kind of claim the ground, plant a flag, get your name on it, but it's it's not the same as an issued patent, right. So a lot of excitement around this topic. Science, unfortunately, has a hard time following our attention span and the speed and rapidity of our news cycle. So, just kind of be patient, but understand this other stuff. And yeah, I think other people, I could just repeat myself, but I'd watch very closely for people that are collaborating with the original authors. That's the kind of proof of the pudding. If they can, if you have people that visit the lab and say, yes, we tested ourselves, or we have equipment, that's really awesome. Other labs saying that they can't reproduce it, I would expect that. I would expect it's very difficult to reproduce. That's true of the vast majority of scientific cases. Yeah, that's what I'd say there.
Andrew, is it true to say that we basically have two ways to know if this is quote unquote real? One of them is reproduction, if we actually see some of the effects, and then on the microscope, if everybody's looking at Andrew's Twitch, we can actually see like the rock levitate. And the other one is if you actually get a sample from their own lab and somebody analyze that like their own samples, right? Away by reproduction, away by like analysis. Is that a fair assessment?
Yeah, that's absolutely fair. But the most efficient route is exactly as Andrew has described, the other Andrew, is verifying the physical samples that already exist. It is incredibly inefficient for the other labs across the world to try to replicate this process because, like you said, this is arts and crafts. It's very difficult to replicate some of these processes. They are subject to a lot of process variables. And some of these process variables were not well described in the papers. And so there's a lot of ambiguity left to the people that are trying to replicate like myself. So I don't expect any chance of success. I mean, the odds that I can show it are very, very low because there's still some question marks about some of the finer details. So I would much rather see those physical samples that do exist from the original authors make their way into the hands of people that can analyze them. And then once we know that it's physically possible, that this effect is in fact real, then it's the job of other groups around the world to do that replication and show it's repeatable in nature. But yeah, it's just a matter of efficiency. And I think that the people trying to replicate without the knowledge of the original authors are going to have a tough time of it. And we should expect a lot of negatives. And that's okay. It doesn't mean that it's fake. It just means that it's very difficult to do.
And just to chime onto that point before I think Jesus goes or someone else, if this doesn't pan out, do not come away from this experience thinking, what a hoax, room temperature superconductors, it's never going to happen, forget about it. Not at all the takeaway here, right? Not at all the takeaway. I think it's the opposite, actually. It's that science is a collaborative human enterprise that spans generations of research scientists. It's artisanal knowledge passed down from generation to generation. And it's something in which, in the words of venture capital, it's something in which humanity gets a performance fee, right? This benefits everyone across the board. So this is not the Super Bowl of superconductivity, right? There's been other previous high-profile discoveries that have been later retracted, but the march of science goes ever onwards regardless, right? So for people who are just wondering about this stuff, this is one story in a field that is many decades old and has a lot of potential. It could point at some really new, interesting lines of investigation. And if it doesn't, then that's still a win, right? Experiments only fail if you don't learn anything. And so our knowledge is constantly growing on this topic. So just don't be too heartbroken.
I want to give Robert a chance to add to this because I know you have something to say on this topic. Robert, if you can hear me, and if you cannot,
yeah.
Yeah.
I posted a thing in the chat just showing kind of the recent progress in superconductors and like over the timeline since they were discovered 100 years ago. And we are very close just with the hydride-based superconductors. And obviously they have high pressures that are required too, but there's possible ways to like engineer around that. Anyway, so yeah, I agree with that. And also just improving cuprate superconductors. We haven't really commercialized that totally yet. Like we're still building ITER, which is the international project to develop the first like break-even like tokamak fusion reactor. We're still building that with the old superconductors. So like we haven't fully used even developments from the 80s, and it takes, even if this is real, it would take decades to fully like utilize this. And there's still a lot of ore to mine technically to deploy superconductors.
Just add some color to that picture, or did someone else want to go first?
I just want to say something real quick because Alex had asked about it before. So regarding like the professor I talked to, I asked him, and this is kind of the point you guys are making. I asked him specifically, "Are you planning on replicating this in your lab?" And he said, "I'm not going to replicate it until they send me a sample and let me actually test the sample first for superconductivity." So that was one thing which I found interesting. And the second thing was, so he kind of seems like he thinks it's not worth the time to try to replicate it. Is like the vibe I got. And the other, unless he can test it. And the other thing, I'm not sure if he was in Korea for the material science conference, but I emailed him as soon as I heard about this, which was pretty much like almost the night that I guess like I first heard about it from an A16Z investor, I think. But yeah, I immediately emailed him and he was already in Korea. So I suspect that he was just there for the material science conference as well. And one other thing which is interesting is not just him, but also the other professor I spoke to, who's a physics professor. Both of them kind of seemed like really tempered in their expectations. So they weren't as excited as I was, or like a bunch of people on Twitter about like, oh, this is the one. They were more like, this is better than most, but we've seen a lot of things like this in the past that ended up being retracted or not exactly working. And I think even if this is not the one, like we get closer and closer every time. This is a very revolutionary technology.
Yeah, just to add on to that, so ITER, the plasma thing in France, it's using superconductors, but it was designed in 1980s, basically, so 1980s technology. Fusion companies today, the one that I work at, and most of them like Commonwealth Fusion, we all use what's called REBCO tape, which is rare earth bearing oxide. And just to understand, how much engineering improvements go into this kind of thing. So that actually was discovered in the mid-80s as well, and it won a Nobel Prize. But for a long time, the material was far too brittle and did not perform well in high magnetic fields. And so, there's been more than 30 years of engineering improvements to bring REBCO HTS tape, as it's called, to the point where it can be industrially relevant, right? And so, yeah, so I think people, that this hits some virality. I think it has a lot of optimism in it and deserves attention. But yeah, I would second that motion of sort of, let's be tempered in our expectations and cognizant of the long, history of progress in this field. Just for context, I mean, when superconductivity was first discovered, people never thought you could get this anywhere above 4 Kelvin, right? They were like, okay, this is extremes of temperatures. This is a thermodynamic limit. This is a very bizarre phenomenon in nature. The fact that we've been able to get this happening at higher
4 Kelvin
temperatures
is just above the absolute zero, right? Like it's very, very low, just for
negative 270 degrees Celsius, right? So it's almost as cold as you can get, 4 degrees warmer than as cold as possible. So this has been a field of defying our expectations again and again, and people, so now people say, well, look, we've had these higher temperatures, and just people see these plots floating around. The big thing here is that people reach higher and higher temperatures with these materials, but the most recent ones have done so at extremely high pressures, right? So pressures on the order of say 1 million times the pressure of the atmosphere, which is difficult to package in a consumer product. I'm pretty optimistic. I'm pretty bullish. I'm reserving.
Thanks, Andrew. I want to get to Mark.
Just really quick point, just because it follows on this. So I agree with a lot of what he said, but two things. So first of all, at the same time, it took longer in the past, but right now we have the way they solved things in the past as examples. So we know that certain things can be issues, and we have like the way that they were solved, plus all the ways that people tried that may not have worked with those materials, but could very well work with these materials. The other thing that I want to mention is one of the things that really caught my attention about LK99 is that they have a theory for exactly why it works at ambient pressure that makes a lot of sense, and that is the copper substitution straining the lattice, right? And that to me made it at least potentially credible as a theory.
Yeah, it's an interesting take. I think there's one thing in the
Andrew, could you just have Marsh up, because Marsh has been waiting to speak?
Well, you all can go on. I can wait. It's fine.
Please go ahead. We already interrupted the flow of thoughts here. Marsh, I want to hear from you, and then from Robert there.
And Young, I just wanted to say he has his hand up.
Yes, and as well. So Marsh, please go ahead. Tell us your thoughts here.
Okay. So I mean, I've been really interested since I first heard about this potential development, and of course, we all expect to be disappointed, but at the same time, it's really, really exciting just because of the incredible potential of this material. I was reading some of the earlier PDFs on Archive, and I noticed it looks to me like an error in the y-axis label on one of the graphs. So I emailed the email addresses of the team in Korea that I was able to find, and I said, figure 5 on page 9 looks like the y-axis may be possibly correct. And on that chart, it showed 0.1 times 10 to the negative 2 ohms per centimeter as the approximately the superconducting resistivity. And I emailed, I said, that's not really that super of a conductor at all. And it doesn't match any of the other numbers that they had published at the time. And I didn't really expect to hear back. I know these guys would be super busy, but I did hear back from Kim Hyun-tak. I apologize if that's not the right way to say his name. But
so Hyun-tak Kim is the author, the guy who published the second paper, also the guy with the credentials who came in with the high score. Him, right? Is that who replied to you?
Yes, that was my understanding as well. He replied, thank you so very much for your good comment. We're going to check the data one more time. We think in changing the data, the dimensional parameters was messed up, et cetera. We would like to show the true data in the attached file. Now, okay, I'm not in the habit of forwarding personal emails that people respond. So I'm not going to disclose this thing, but he attached 2 slides, and one of them was already disclosed at the conference in the other day. What was that called? The MML 2023. I think there was a leaked camera photo, and I see the same graphic. So I'm going to put out a higher resolution version of that in the nest here as we speak. So
awesome.
Apologies if I sound a little distracted here because I have to get to work.
Yeah, you have to wrestle with the Twitter on. You add it and put it up for us.
Yeah. So I'm on my computer and then I'm on my phone because I.
So Marsh, while you put this up, I want to hear from Sung-hyuk, and then please put it up, and then feel free to add some more commentary to the slide after you add this. Go ahead.
So I want to say 2 things. The one is that what we say HTS, high temperature superconductor, it really happened in 1986. And the group who discovered HTS won the Nobel Prize in Physics very next year in 1987. So while the success probability is low, it did happen in the past. Like in 1987, more than 50 groups in the world replicated and improved upon the finding, and there was a conference dedicated to it, and it was called Woodstock of Physics at the time. And on the 20th anniversary, New York Times did the recap of the so-called Woodstock of Physics. It is a very fascinating reading. If you haven't read it, you should have read it.
Awesome. While we wait for Mark to put it up, Mark, go ahead.
Also one more thing that so as I pointed out, it really happened in 1986, so it could happen again. But I also have the low probability of this succeeding, so I want to propose that all the speakers in this space share their personal probability of this working out. Like Alex, you can call the individual people and ask them the probability.
Before we get to probability, I want to hear Marsh put up the slide, and then we can talk about this, and then definitely we can get to kind of the juicy bit where folks here with experience can give their gut feelings about this, although it seems that at least some of it we already kind of get summarized.
Okay, I put the slide in the nest. It's the one furthest on the left right now. It is a graph of measured volts on the y-axis, microvolts, and applied current across the lower axis, milliamps. That's a 1,000-fold difference in ratio, but it's what you would expect if you were attempting to measure very low resistivities. But one thing that concerns me about this is there's noise in the data.
but most of the data points are below 0.0. So there is a bias to this at the microvolt level. It looks like maybe 1/20th of a microvolt, like half of a tenth of a microvolt, so 50 nanovolt negative bias in their meter reading. That seems like a reasonable amount of error for a high-quality voltmeter to read. But I don't see any signal whatsoever here. I mean, I know it's supposed to be a superconductor, but when the x-axis is modulating the current between minus 30 milliamps to plus 30 milliamps, I would expect to see some kind of correlated noise there, even if the probes were just touching each other and measuring each other. Like in another slide, I have a picture which looks a lot like pictures we've seen before of, it looks like maybe a semiconductor wafer probing apparatus with a big aluminum disc, or maybe steel disc, mass tech, and then 4 gold probes touching the surface of a large square sample of some kind. The probes are 4 probe points in a linear configuration. So this would be probably a 4-terminal Kelvin type of measurement setup. And if this is what they use to measure the data in this graph, it's not encouraging to me, to be honest, because this is consistent with maybe one of the probes just not touching the sample very reliably. Like if you had a probe lifted off and the voltage reading was not actually registering the sample, sure, I mean, you could get a very small nanovolts type of noise in the voltmeter. It's not a cryogenic voltmeter, I assume. And it seems completely uncorrelated with the x-axis of, 30 milliamps is a lot of current, plus minus, if what you're measuring is in the nanovolt range. So, yes, it looks like an extremely low resistance material, but what would encourage confidence a lot is if they said, oh, well, we used our same setup and we measured, an existing superconductor, or, high purity gold, or, we touched the probe tips together and zeroed the apparatus, and then we measured the superconductor and we saw some kind of difference. So that's all I have to share. I hope it's interesting or helpful to other people. And
I want to say it's most interesting, and I want to give folks on stage the chance to react. Folks who understood much of this, a bunch of it went above my head. One thing I would love for you to kind of recap, if you could. This graph is the fixed graph that Hyun-Duk emailed you, where on the second paper this graph does not make sense. Am I getting this right? The graph that they published in the second paper could have been potentially like maybe an error or a hasting error, and this is the graph that you got with like the fix essentially. And the same graph was presented at an MMO conference with the new y-axis. Am I kind of recapping this correctly?
There's a very similar graph. Actually, this graph looks like it's also in the 12008 PDF paper, the 3-author paper. It looks like figure 1B. And this is what I just can't reconcile. Like figure 1A looks, with the applied current measured volts, it's showing a phase change. Now look, I'm no physicist. I'm not even a DE. I'm just a really interested experimenter with a 6.5-digit DMM, who's played with these kinds of measurements a little bit. But I can tweet that just for reference. But in the 2307-12008, the 3-author paper, figure 1A, how is that not evidence of a superconductor? I don't care about the Meissner effect or all these, or the, what was it, a density change or something like that. I mean, if it has a very strong kind of step response to temperature and applied current, where it literally flatlines the measured volts as the applied current is varied, it's hard to say what that would be other than they're measuring a superconductor. So there's a lot of hope and conservative, not wanting to be disappointed. But I just don't. Some of the charts that they've published, it's hard to explain those any other way than they are seeing some kind of superconductivity or material phase change that is dramatically impacting the conductivity of this material.
Hey, this is Ken Condon. I'm one of the Sparkies here at Varda Space Industries. By Sparky, I mean electrical engineers. And I was curious why you think the current source steps should be correlated with the voltage measurement. A lot of times those are, I'm not familiar with their particular setup, but additionally, if you're measuring like something with a really, really low source, you're going to have noise on your reference of your current source. And that's going to be statistically independent from thermal noise on your amplifier for your voltage measurement response. So I actually wouldn't normally expect increases in your current step to be correlated with kind of like noise changes on your voltage, if that makes sense.
Yeah, I get it. But let's say you took 4 probes. You know about the Kelvin 4-wire measurement
Yep,
connection.
very, very familiar.
Let's say you took that setup and you just touch the tips of all 4 probes together. So there should be no sample at all. There should be 0 resistance. I think in those circumstances, modulating the applied current plus minus 30 milliamps would probably show something on the nanovolts scale. On the other hand, I may not have used equipment that's high quality enough to not show some type of correlated noise. I'm just relating my feeling. That if you're measuring down at nanovolts, sometimes you just move the wire of the probes itself a little bit and you get big changes at the nanovolt level. That's my experience. But again, I've never used what looks like a wafer testing setup, and who knows how accurate. What kind of shielding did they have around this measurement? So if somebody has more experience with fancier equipment than I have access to, please, I'd like to be wrong about this.
Marsh, I want to slide in here, Ken, before you continue to react. Folks, it's an hour 40. We've covered the human drama. We've covered kind of the events as much as we found. We had Sangyuk here going and translating the right places. So we've tried to give you as much information as we were able to sleuth around the internet in this kind of one summary. So we'll definitely summarize this. Now we're going into like extreme nerd mode, and I'm here for it 100%. Like, this space won't stop until we have folks debating and discussing, and hopefully we'll find some stuff. But if it's not for you, obviously that's understood. I just want to shout out the folks who are currently on stage. Maybe some of them won't have the interest to stick around, which is fine. But yeah, please, let's go ahead. Let's try to find, if there's fire beneath the smoke, can go ahead, and then Andrew, go. I think you had a direction.
Yeah, totally. I would, I forgot who said that, but I think it was a well-reasoned statement of, trepidatious optimism, but also some confusion over measurements. I think figure 1A in the 3-author paper I'm looking at right now, the measured volts is in millivolts, and the scaling, interesting choice of scaling, maybe a logarithmic scaling on the y-axis would show a lot more interesting stuff here, just because, yeah, just some stuff missing there. I would also, so in terms of, things in the paper that are a bit off or whatever, here's something that I haven't heard a lot of people talk about, and it's mainly their measurement of heat capacity as a function of temperature. So a very consistent result with superconductors is that as you cool them down, and here, I'll just get some background first. So heat capacity refers to how much energy something can absorb for its temperature to go up by 1 degree. And really what it's doing, it's measuring the available states that electrons can occupy in that crystal lattice, right? And you kind of think of it like, as you get colder and colder, those available energy states become frozen out of what's accessible, and so you have a declining heat capacity. Now, a really consistent result with superconductors is that as you approach the transition temperature from a high temperature cooling down, you're measuring the heat capacity, how much energy does it take to cool it down by another degree. As you approach the supercritical temperature, you get a spike in heat capacity. And what that people usually interpret that as meaning is that suddenly there's this energy state that tons of electrons can fall into, that can absorb energy and fall into. And that's kind of like very much tied in with this sort of canonical theory of superconductivity, which is called BCS theory, right? And it's all about electron-electron coupling. So in the 3-author paper, something to kind of just point out for people is that they failed to measure that important result, showing the increase in heat capacity as you approach a critical temperature. And they didn't take that to say, does this call into question whether this material is a superconductor? Rather, they said, this is a support for an alternative theory of superconductivity that does not involve electron-electron coupling in the crystal lattice, but electron-phonon coupling. And so that's in the weeds a little bit. But just to point out, so there's some measurement issues, there's some data visualization issues for sure, as we mentioned. There's this other, we didn't measure this super important property, and we choose to interpret that as supporting a alternative theory of superconductivity. And so that's another kind of like a strike against this, and that's one reason I think you maybe find scientists that just dismiss this out of hand, because they're like, oh, well, these guys messed up. They're trying to push some not as popular interpretation. So yeah, that's another thing I just put on the table of what are the pros and cons in this result.
So one thing that jumped out at me, and you know more about this field than I do, but at least I was interested in knowing what the carrier mobility would be. I don't know if that's what people go for first or early in terms of characterizing a new superconductor, but the fact that they're talking about electron-phonon coupling, it would be quite remarkable if the carrier mobility turned out to be related to the speed of sound.
Yeah, I haven't seen anything in this paper on that in particular.
Can I ask for the audience, what would the speed of sound have to do with anything? That sounds like it's something that would come out of left field.
But speed of sound in the medium, because that relates to phonons.
And phonons are quantized
mechanical vibrations, yeah, generally quantized.
I'm not as familiar with that being a sort of key figure of merit in measurements of superconductivity.
No, not at all for things. And that would be like a remarkable thing, and that might explain why they didn't talk about carrier mobility, because they're probably still working on it, if there's anything to that.
All right, folks, the nerd discussion, the one that goes way above my head, I very appreciate it. This is recorded. We're going to put it up and we're going to analyze it. I think I want to thank Marsh for the absolute alpha here, right? We have email correspondence with the team. We have some unprecedented kind of discovery about, a potential of this being actually true. I want to say that one of the things that Sangyuk and we talked about is going around the room by speakers and just like giving some amount of probability, given all we've heard, given the very weird way those papers were published, the multiple papers, given the missing pieces that we're now collecting together. There's 3 papers with different measurements. However, there's a bunch of stuff, given some folks on stage here who actually try to replicate, and some other folks follow other replication attempts, given some folks who talk with the researchers in MIT. I want to go around the stage and to give folks a chance to kind of put their chips on the table, if we will, and give maybe some amount of probability of whether or not LK99 is actually a room temperature ambient pressure superconductor. Feel free to go unmute yourself and say, otherwise I'm just going to call out some names. I think Sanghyun, let's have you go first. After your research and you talking with friends and doing like on the ground translation, where does your probability lie in having this be actually a superconductor?
Can you hear me?
Yes, sir.
Yeah. Okay. So there is a thing called the prediction market. It says that you should vote about values, but bet about your beliefs. So my belief on whether this will turn out to be successful varied a lot in the last 4 days, but my current probability is 15%. And when I say this, people around me are surprised because they think it is too low. But to me, 15%, like 1 in 6 or 1 in 7 chance of the changing the world, is really high. And they think, if it is 15%, why are you spending all the time on it? And I don't understand that objection. So also, there is a prediction market on the internet called Manifold, and I note that their current market price is also 15%.
I will say one additional thing about the prediction markets, given that folks have, playing money in there. There's poly market with actual money, I think, and manifold as well. For folks who want to follow along with like the latest and greatest news, that's also great research, right? So you can definitely follow the folks on stage, and I encourage you to do so. Follow Andrew, follow ATOPI, follow Marsh, who just joined us, Jesus, Eli, Andrew, and Sanghyun, and Ken, and everybody here on stage. Follow me if you want. I'll cover this as well. However, the prediction markets have people who are betting this. There's quite a lot of money there, and so they usually also rush out kind of the news first, and that's also like a very good resource for you to stay up to date. So 15% from Sanghyun. I want to get to ATOPI next because he was first on stage. Give us your probability.
All right, so I don't know anything about the science, all right? I know people and I know academics, and you build a stock of credibility, through a lifetime of research and credentials so that you get taken seriously. And these guys decided to incinerate their entire lifetime credibility on this, right? The entire lifetime credibility. You spent like 30, 40 years building this up, and you build up this enormous poker stash, and you decide to put it all on one roll of the roulette wheel. That says something, right? So I'm thinking it's like 80% that you can detect some form of superconductivity in there. I'm thinking that, to get it into production, like to get it into like a thin film material is going to be tough. And, manufacturing and mass is going to be tough. I'm thinking like those things are going to, we're still going to have like real challenges before we actually see this in product. And for me, the reality of the situation is like you only know something when you get in the product in your hand. So I think that's going to take a couple of years. I don't think that's going to get sorted out. And we're going to be in this muddy phase for a while, and then we're going to argue like it's not really the kind of superconductivity that we expected, like blah 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 blah. But I kind of think it is. So I think these guys incinerated their stock of credibility for a reason, and all of them did it at once. Like it's done. It's done. Your credibility is done. You put all of it down on this roll of the dice, and so that's there. Yeah.
That's a very passionate 80% from ATOPI. Andrew Goto, I want to hear from you next if you don't mind, and then we'll go.
Yeah, I appreciate the sentiment there, putting your reputation on the line. Warren Buffett has this great quote: "Reputations are built over decades, and they can be lost in minutes." I wouldn't doubt that these researchers believe their result and that they're eager to put it up there and all this kind of stuff. I think that's independent of the result having a high chance of success. I'm personally, maybe just because I have seen previous retractions in the field that were quite high profile at the time and failures to reproduce and so forth, still more in the 10, 15%. People ask, why would you be so interested in this thing if it has a 10% chance of working? Because a 10% chance of the world changing is a huge deal. The expectation value on that is massive, right? I would also second the motion that if this does pan out, there's a long road ahead to get this to work, right, in industrial applications, right? So having it resilient to strain, having it work within high strength magnetic fields, getting good current density and so forth. But if that happens, that's a win. Like count that as solved. That's just a matter of time. The big stochasticity here is finding the right location in the space of possible materials. And I think there's some good points here. Maybe this isn't strictly a superconductor in the way we think about it. It could still be a very interesting material, and it may be very suggestive of types of crystals and material compositions to look into the future as well. So it's not an all or nothing in my mind, but that being said, it's still be in the sort of 10 to 15%. This is going to hit kind of range.
That's great. Eli, you want to go next?
Sure. I have to break it down, though, in a number of different ways. 2/3 chance that they actually had their hands on actual semiconductor-ish materials. In other words, it might not be a classical type 2 superconductor, but it displays at least some of the properties. A 1 in 3 chance that somebody replicates it, and a 1 in 10 chance that this is what winds up being a commercial material, but a 2/3 chance that it leads to, if it ever is at all a superconductor material, so conditional probability, a 2/3 chance that it does at least directly or indirectly lead to a commercial material in less than 5 years.
That's awesome. I want to hear from, let's see who on stage. RoboBeat went down. Ken, you came up, you want to give us your probability?
Yeah, I mean, I am an electrical engineer by training. Solid state chemistry is definitely not my field. So for a rough probability, I would have to put it at the prediction market value of around 15%. Probably a little bit lower because I think people tend to overstate the probability of things that have positive outcomes. So maybe lowering that down to 5 to 10%. But one thing I will note is when we're in spacecraft engineering, very often we have probabilities in the 1 in 1,000, 1 in 10,000 chance. But what we spend a lot of time thinking about those probabilities because the expected value of those events is very high. You can lose a spacecraft. You could cause harm to individuals or capital. You could lose your FAA licensing. And because of that, I know that even things that have a low probability of success are extremely valuable to work on. And you really have to think of the expected value. So the expected value of this outcome is extremely high. So it deserves all the attention possible until the probability is driven near 0.
That's awesome. We just had Ben come up, and Ben was here in the beginning. Ben, have you heard the question? Yes. And what's your probability?
Yes.
Give us your thoughts.
Thank you. Yeah, I love these prediction markets. I'm heavily on manifold. I tend to agree with Eli that I think there's a pretty high chance that it's superconductor-ish, because if it's this new quantum well superconductor, whatever they define it as eventually, I think something around 50 to 60% chance that they have superconductor-ish material. I would say something closer to 15 to 20% that it is replicated in that sense that a lot of these prediction markets want to find out, that it is replicated as a superconductor as they described it in the paper. So a lot lower. Those are my estimates.
Who did we not get to? I think Jesus. We didn't get to yet. You want to give us where you stand?
We're so back. Just kidding. I want to believe that more than anything, but I kind of, so there's nothing physically impossible about this, which is what I like the most. And even if this one isn't the one, I actually believe that this kind of weird, this unusual theory they have for why it works could actually lead if they delve further into the theory and go and kind of follow this line of investigation. I think this could lead to the one. But most of the people who I know that are like absolute experts on this, they don't seem super excited by it. ADAPI made an amazing argument, I think, which is like, why would the researchers like fabricate this? I definitely don't think it's fabricated. I think they probably believe it, but there may be some issues with the data essentially. So overall, I'd probably go for like a 10%. Not to be a doomer, but something like this. But I actually do think this is inevitable, like eventually.
Andrew, go ahead.
Okay, yeah, I'll take a slightly different perspective. Like a lot of great opinions here. So I think that if it is actually real physics, whatever the percentage is that it is actually real physics, that humanity has realized a superconductor at this temperature range, I think that it is a 99% possibility that we will commercialize it, that we will find a way to make this useful, to extract economic value from this material. So it's probably, it feels to me like a 10 or 20% chance that it's actually real physics. Like I've done a lot of experiments, echoing Ken's statements. It is easy to mess up the physical experiments. But if this is a real phenomenon, if this is real physics, then I have absolute confidence that the capital markets will grab onto it and integrate it into our economy. And so let's say 20% that's real physics and 19.9% that we will figure out a way to commercialize it and make it useful for humanity.
Everything I heard on stage so far, from the haphazard kind of multiple paper release to the scientists involved, and they're working on this for some of them 20 years. The professor emeritus, Choi, or chair, I think Choi, who's kind of on his deathbed, pretty much like asked them to kick this up again, or something like this. Are you doing a thumbs up?
Yeah. Because you have to understand that there's these like little weird scientific cults that build up over time, and they often end up in like this kind of like circular motions of like getting caught in like analytical traps or like local minimums, and it happens all over the place. That's the whole reason you have like peer review and like stuff. You have to get stuff out of your local area and get someone else to review it. So I think like all of that stuff doesn't matter. Like the whole like the 3-person group together from Korea University is completely like meaningless. Like the people who matter in this are like Kwon and Hyung-tak, who came in from the outside, who joined in later, and were not part of this like cult movement, basically.
Yeah, and so the fact that so let me just like finish up my thought here. The story about this, were like it's not just something that they came up with. Like they've been trying at it for multiple times. I think some folks said like 1,000 different tries, etc. The external scientists who got either attached to this or were required for money to flow or like for actual patents to lend, and the fact that those external scientists, like you said, are potentially not part of this cult, right? It's not part of the name, etc. And they're still willing to put their reputation online. Those all signals of, hey, we could have something here. By way of probability, I'm just gonna go crazy, and I'm in the we're so back camp. Let's put it at 40%, because I want to believe. Look at how much interest this generates. It doesn't matter if it replicates or not, because we're not putting money. I'm not putting money unless I'm putting some money for it. However, the potential outcome for this is incredible. The excitement that this generates is incredible. The other stuff that humanity kind of progresses towards while we speak, and the insane pace of innovation that happens over there means that even if this is not like fully baked, like some folks said here, even if they have like directional interest, I wanted to follow up this with a question about the quantum wells and different type of stuff. However, the other progresses we're making in computational power for humanity seems to me that this could also help us progress there. And so I want to put myself at 40% and just like strongly believe. Marsh, go ahead next. And I think folks we're at exactly 2 hours, and this has been very fruitful. So after this, Marsh, I think we'll do like a round of applause for folks on the stage, and then we'll close out. So Marsh, go ahead, and feel free to also shout out.
Okay, so I'm asking this, and I don't want to come across as cynical or jaded or anything, but I think it's a question that a lot of people have, and that is, how is it that there are 6 different PhD researchers on these papers from 4 different institutions, and we're still asking questions about whether the data is accurate, whether we're seeing correct voltage readings, whether we're just some of the basic science measurements?
Okay, so I have a response to that, which is that they didn't have money. So the funding was very limited. They may not have had money for all of the equipment that they needed. And in fact, like, they have photos of the ESR machines, like they're using like maybe secondhand ESR machines. They needed to pull in Kwon for the squid machine. Without Kwon, they would not have had the squid machine. So they had a very limited budget. Like these guys were like really like doing artisanal stuff. So.
And to this point, I will highlight Elza's pinned tweet on top, where there's like a vendor of ingredients says that they're like sudden surge of lead orders in China is happening, and so many people are trying to replicate and potentially get to some of these measurements. So Marsh, I hear you, and I think ATAPI like presents an interesting theory of why not. Just materials could not, so they may have like either run out of money or operate in a very limited budget. But now, with the world believing, and what I've heard from all of you on stage is like, we're in the above 12% for most of you at least, which sounds incredible to me. I want to start closing this out, folks. I'm starting to close my voice. It's way past midnight and it's a Monday. I want to get to some folks. I want to start with Sung Hyun, and feel free to to tell us what you think, and if you want to plug something, this is the time. And folks, definitely follow Sung Hyun.
Also, that I think the archive upload may have been the most successful clickbait in the history of the internet. Like, I mean, if they were too poor to buy the necessary equipment, now probably the measurement equipment money is no object.
All right, so let's go and say our bye-byes, folks. If you want to plug something in, this is your chance. There's a big audience here listening. I will say just one thing before we kind of start naming names and saying goodbyes, is that all of the folks up here on stage are in this like Twitter list that we're trying to collect, and we will be following different updates in there as well. And if things change, definitely expect more from this group. I want to get to Andrew Coate. Feel free to plug whatever you have and tell us your parting thoughts here, and then we'll get to Ben.
Great, thanks, guys. Yeah, appreciate the space. Yeah, not going to plug too much. I'd say just reach out. If you're in San Francisco and you're interested in discussing artificial intelligence as it could apply to material science and the future of humanity, get in touch. I like to host discussion groups once a week on these topics. And any way this shakes out, it's an amazing time to be alive. And the number of miracles that our modern lives are built on that provide convenience and leisure time and abundance in the material world is incredible. And be thankful that scientists are out there taking these reputational risks, putting their chips on the table to try to get these things out there. So yeah, thanks again for the space, and let's stay optimistic.
Thanks, Andrew. And also, folks, Andrew writes a Substack, I believe, so please go subscribe and read his stuff. Thanks, Andrew, for the great inspirational stuff. I want to acknowledge Danielle, who we tried to get up here for a while in the group chat, and I want to hear your numbers if you want to speak. Go.
Hi, guys. So yeah, people started to split out two different numbers between like the likelihood of something being superconductor-ish, which I guess means, significantly better conductor than copper, resistance near zero, versus what people call like a traditional superconductor, which I guess means basically either the strong form of the Meissner effect or some flux spinning like in a type 2 superconductor. And I just want to make the strong case that like the necessary thing for it to be a superconductor in my book is that it is a superconductor. Its conductivity is high. And I think that it seems more likely than not that they have actually found something, but it also seems definitely true that they have never had the money or the resources to fully master the baking of this. So I've seen so many different people from around the world, being completely ready to say, is it fake? Is it not? It replicates, it doesn't replicate. Oh, it doesn't replicate. Oh, it's over, like, oh, it's diamagnetism. Like people don't know like how to bake it and make the same thing. Like there hasn't been samples but it seems quite likely, as many have made the point, that they have found something, and that's going to get investigated. And I think that this is way more real as a matter of physics than people have patience for in a sort of 1 to 3 day consideration of like a tension cycle. But I'm super excited. I think this is one of the most exciting discoveries. It's likely to be one of the most exciting discoveries in solid state physics ever, and it could be pointed towards the direction of developing a useful superconductor. Although I think the chance that we would use this without changes widely is almost nil. Well, this is always just a starting point, and I'm very excited and still very excited to see what happens next. So that's it.
That's awesome, Daniel. Thanks for coming up and giving us your thoughts here. I want to get to Ben next. Ben, feel free to summarize your point and feel free to plug in whatever you want and why people should follow.
Yeah, nothing to plug in particular, but yeah, material science is awesome. I mean, I really hope this brings attention to it's kind of a niche field in between chemistry and physics and a bunch of other stuff, but this is like really core material science stuff. So it's pretty cool to see people like discussing and learning about it. Yeah, I'm excited to see where this goes. I really just hope they send this to somebody who can put it in an electron microscope. I think that's like really the first step to figuring out what it even is. So someone should do that, definitely.
Awesome. Eli, you want to go next?
Sure. So kind of like really on the same wavelength as a lot of other people. I come at this from a number of angles. I'm material science adjacent. I do stuff in nanofabrication by a whole wide variety of methods, and I'm kind of looking forward at some point to trying to integrate parts of this, if anything is verified to be here, because I won't be on it quickly enough, and I hope other people settle this first into my nanofabrication tech stack. I do want to kind of like plug that. It is directed to things that can be part of near closure self-replicating systems, and the important thing about that is that's a technology that once it's established inherently scales, including to global size problems, and one of the really important ones, not the only one, is removing excess carbon dioxide from the ocean and the atmosphere, because it's becoming clearer and clearer that the risks of climate change have actually been underestimated, and we need a better plan than we have, both for that and for supporting civilization renewably and regeneratively. And we can do that, and with something along the lines of self-replicating systems, we can actually rewild most of the world, 90% of the world, and have a human population that's probably on the order of 20 billion plus, right? So the future is very different than most people imagine, if we can get through this difficult patch that we're in. Let's
go. It was a great finisher. Thank you. Jesus, go ahead.
I think even though I said 10%, I still think that that's kind of like a really high expected value sort of bet, because this is a technology that it's profoundly revolutionary. I think it could change almost everything on Earth. So the thing I'm most interested in is like Andrew mentioned that there's going to be like a reading group in SF. I live in SF. I think this stuff is super cool, and it could maybe be the basis for like the next Intel. So I'm also really interested if anybody's actually trying to replicate it or something like this in the city. Yeah, I'm curious if anyone's doing that, because it's something I'd love to get involved in personally.
Right. If you guys have replication attempts in San Francisco, add Jesus to there. Marsh, go ahead. Marsh, if you're still with us.
Oh, yeah. Thanks for the opportunity to speak to everybody. This is a really interesting discussion. I know we're all just really anxious and excited to hear of the first news of somebody who says, I got it to work, or, we tried everything in our, highly professional lab and it can't make it work. That would be news too.
Yeah, that's great. Andrew, and then ATPI, and then I'll close us out and go to try to sleep after this. Andrew McAuliffe. So Andrew, before I give you a finishing thing, I did have a question in the audience who asked, what's next for Varda replication attempts? Are you going to keep going? And what are you working on? And then feel free to finish us, with the final statements or something.
Yeah, absolutely. I agree with a lot of that, the points that have been made, but I think the most important thing to emphasize is finding out if this is real new physics. If this is actually room temperature superconductors, the entire economic landscape of humanity changes. This is an inflection point. Even if it's 1% possibility, the expected value is still positive. So to me, the most important thing in the world is to verify that the actual physics are valid. My replication experiments are insignificant in comparison to figuring out if this is a real thing. If this is a real thing, then the resources of the entire world will pile behind commercializing this. We will put resources behind the development of this idea. But first we have to figure out if it's valid. So what I'm doing is not as important as actually taking the physical samples from the authors and proving it. If we can get to that proof point, then everything else is just engineering. If we can de-risk it to the point where you take it from the science level to the engineering level, then that's the inflection point. So I feel like that's what we have to do. My experiments are not likely to result in success on the first or second or fifth try because of all the reasons stated before, but it does call a lot of attention to it. It emphasizes the importance, the economic value of the thing that we're looking at. So if the plug is, if anyone in Los Angeles wants to look more critically at the materials that we produce to do material characterization, we would love to partner with the professionals in the field, put the physical samples in the hands of the people that can pass judgment. That would be wonderful. We'll keep pushing forward. We've got a couple different partners already, and so we should have physical samples done by Tuesday. And so at that point, we'll pass them off to people and start evaluating the actual characteristics of the system and start turning these theories into measurable physical samples and measurable numbers.
Quick mention.
One second, please. Andrew, I know I said like we're closing down. However, I will be remiss, I think is the word, if I won't ask you about space, because one thing that excites people about this is the potential for changing energy, but also one of the things that people look up to is space. And I personally never heard of larger space before you started this. So pushing back on your attempts as you kind of try to downplay them, I think there's many people, and we've seen the excitement around Twitter, who try to follow you, take this thing, and try to kind of run with this and publicly. And I think this inspires a lot of people. And first of all, thank you for doing that. And second of all, thanks for hopping in the space to chat with us. Please continue. And number two is please give us like 2 minutes on Varda space. I want to hear. I haven't heard before. I think space is very exciting, and there's plenty of people in this audience who, even if the superconductor stuff doesn't replicate, we'll definitely want to hear about Varda space. Can you do us this favor?
Yeah, sure thing. I'll try to offer a balanced opinion here. Is that I'm excited about this because there's very little materials that make sense to do in outer space. There's 5 or 6 that really make sense, that produce positive economic outcomes. That's what it's all about. At the end of the day, you have to make a profit. You have to push a value into the market for anything to be worth anything. And so we will never make these things in space. We should be trying to make superconductors for $5 a pound in the terrestrial market. What we're doing is a very niche market on the Varda side. We're trying to develop technologies to advance humanity into the solar system. We're trying to figure out where novel physics can be exploited, turning off one of the fundamental forces. So my day job is crystallization and figuring out how to, if we can turn off one of the fundamental forces of the universe, realize economic value in a particular field. It's a very similar equation on the superconductor side, but the impacts are much, much higher. So this is inherently interesting to me because it's humanity level impact. We're attempting to make an impact in a particular market, pharmaceuticals, but this technology has the ability to impact the entire course of humanity. This rewrites some of our basic operating principles about thermodynamics. This unlocks the ability for engineers to operate with a new class of materials. So it is incredibly exciting. So I think how I would summarize it is it's really important to not lose sight of the fact that you have to push economic value to mankind, however you do it. When we look at these basic scientific advancements, you always have to think about how does this advancement translate into market value, into an advantage for humanity, and how are we going to turn this into a product? And so that's why everyone is so excited about this, because the possibilities are undescribed at the moment. They are absolutely huge.
Add to the plug. One thing I might say is right now the space economy is much more fragile than it seemed. As someone who came from SpaceX for quite some time, and there is this chasm of death that the space industry is facing between where we're at right now, where standard commercial communication satellites and similar are being launched, and those are profitable, but only up to a degree before they hit saturation. If we really want to extend our capabilities as a species and really take advantage of the resources in the solar system, we need to expand our space capabilities very dramatically. And not just in what I used to do at SpaceX, not just in the launch, not just in communication satellites. We need to be able to work in space, return materials, change orbits, all of the above. And I think Varda is really attempting to carry us through that chasm in between a society that has a large number of satellites in low Earth orbit and being able to extend larger into the solar system and really do much more than just have flying cell phone towers, like really being able to take advantage of the resources in our solar system by first coming up with profitable use cases for all this launch capability we have. So I really see Varda as us bridging the gap to expanding our resource capability beyond the Earth.
That's awesome. Thanks, Ken, for chiming in, folks. Check out Varda Space. Follow Andrew, Ken. ATAP, finish us off before I say the final goodbyes.
Okay. I mean, I think it's super exciting, and I like the human drama aspect of it. I like the fact that more people are getting pulled into the science, and there's science and then there's production, right? Like the science is only the first hurdle. Production is often an even bigger hurdle. And I'm in biotech. Like something like 9 out of 10 treatments work in mouse models, and you never even get into phase 3. So we have to take it with a pinch of salt, but it's still very exciting to see basic stuff come out. The other thing I'm pretty excited about is that for me, I see that the guys coming out of these 2 guys are basically 100% of their time graduate work was in Korea. And so one of my theories is that as we all get integrated into the internet more and more, we all read the same things and we all get into this like monoculture. And especially in science, that's terrible because you don't get to search out like new nodes on the tree if everyone's thinking the same. So I think it's very exciting that they have, maybe the subculture works, right? The third thing is that I think most of the basic material stuff in this century is probably going to come out of Asia, because I think the US has lost a lot of its like basic materials, like, you know, progress. I don't even think people are aware that the last big basic materials discovery was the high pressure acid leach process for nickel, which basically transformed the nickel market. I don't think most Americans are even aware that that happened in the last like 20 years. And that came out of China. And no Nobels were awarded for it. And it was really a process improvement in the manufacturing of transforming like low grade nickel ore into, you know, steel grade, nickel inputs. So I think it is more likely it's going to come out of Asia. And I think, you know, it's exciting to see.